Hi, I'm Maya, and this is my demonstration of my final project for the Mastering Electronics lab. Okay, so here is my circuit. I have up here a low-pass filter. This here is a high-pass filter, but it's cascaded so that the low-pass output goes into the high-pass. So this whole thing is a band-pass filter. And down here is a high-pass filter that's on its own. It has just the signal input, so this is just a high-pass filter. And down here I have 3 half-wave rectifiers. So how my circuit works is I have this signal input coming from the function generator, and it is this one, it's all carried by the pink wires. That's all the same signal input. So the input goes to this signal input goes to the low pass filter, and then the output of the low pass filter comes down to a half wave rectifier. But it also goes down into the other high pass filter to create this band pass, and then the output of that is carried by the yellow wire, goes down to its own half wave rectifier, and the high pass filter takes in the same signal input as the low pass filter did, and its output carried by the light blue wire goes into its own half wave rectifier circuit. So the point of this is to just sort of the 3 different filters all create a kind of a different, they isolate different frequencies from the input signal. And if this were used with, like, for music, for example, it would isolate different frequencies from the audio, and then each of those different frequencies would be rectified, and it would kind of create a cool distorted sound. And this could be used in like audio synthesizers, and you'd get 3 different notes per sort of input note. So we can see it's hooked up to 2 different power supplies. This one is negative here, this one is positive for the op amps. And first I'm going to demonstrate how my low pass filter works. I have the oscilloscope hooked up to measure the low pass filter, but let's maybe get another one to measure the input, just so we can really demonstrate the input, and hook that up to be the right. Okay, so demonstrate my low pass filter here by, I have it, the function generator set up to put in a 100 hertz sine wave with an amplitude of 0.5, but on Tinkercad, the amplitude you put in is the peak to peak. So it says 1, but that's a 0.5 amplitude, 0.5 volts. And the way I designed my low-pass filter was to have a maximum gain of 5 and a 3 dB frequency of about 1595. So at 100 hertz, we should see that the gain is pretty close to 5. I guess it won't be exactly that, but pretty close. So if we start the simulation, it's going to take a minute, but we can see over here our input frequency, or input amplitude, is 0.5, as we would expect to see. And over here, we can see that it is about 2.5, which again, that's going to be a gain of about 5, like we would expect to see. It's not exact, we can't get an exact measurement here, but that is approximately what it is. Now, if we change this, let's test it at 1000 hertz instead. I'm gonna have to change the scope here. Give that a minute to sort of fix itself. You know what, let's just turn it off and then on again. So we're applying an input frequency of 1 kilohertz, same amplitude. We can see again over here, the amplitude is 0.5, and over here now, it's a little bit closer to, just a little bit over 2, more kind of 2.1, something like that. So the gain is going to be about 4.2, which is exactly, not exactly, but pretty close to what we would expect to see. Okay, so now we can apply a higher frequency to this low-pass filter. Let's put in 5 kilohertz, and we'll see that now this is past our 3 dB frequency, right? So we're going to expect the gain to be a lot lower than 5. We're going to expect it to be about 1.5 actually. So we can see over here that it's at, the input is 0.5 volts, and the output is about 0.75 volts. So the gain is about 1.5 as we would expect to see. So we can see that the low pass filter functions the way that I designed it to. It allows, lower frequencies to pass through and cuts, minimizes the gain for all higher frequencies. And as you get significantly higher, the gain would be, actually lower than 1. So they'd be a lot smaller than even the input signal was. Okay, so now we can look at my bandpass filter to see that it functions the way I designed it to. So we have the low pass filter cascading into a high pass filter. And I wanted the entire bandpass to have a gain of about 10. And the way that works is the gain of this one gets multiplied with the gain of this one. So we know that this gain was already, the maximum gain was 5. So I had to make this maximum gain 2. And I designed it to have the right resistors and capacitor for that. And we can see when I put in a low frequency, so 500 hertz, we should expect the gain to be about 6.5, because the 3 dB frequency of this high pass filter was about 530. So a 500 hertz frequency is lower than that, but not significantly lower. So it's not quite in the pass band for the high pass filter, but we should still see a sort of higher gain. Not super low, but not high either. So I'm going to pass in the input. Here is again 0.5 volts, and we can see that the output is about 3.2 volts amplitude, and that gives us a gain of about 6.47, which is pretty close to our expected 6.5 volts. Now if we check with a higher frequency, this one we're going to expect to see is pretty solidly in the pass band. Let's just change the setting on this so that it's a little bit easier to see. Stop and start it again so it loads nicely. There we go. We can see that the amplitude here is our input of about 0.5 volts as we'd expected, and our output here has an amplitude of about 3.7 volts. So that's a gain of about 7.5 volts, which is pretty close to our expected gain of 7.5 volts, or approximately 7.5. And if we then pass in a higher frequency, we're going to see that this is again out of the pass band, but now because it's higher than what is allowed by the low pass, but it is allowed by the high pass, but the high pass does have a lower gain, so we're going to see that the gain is going to be lower when multiplied. And again, change this setting so we can see this. We're expecting the gain to be about 3. So input is 0.5, and the output is about 1.5, which gives us a gain of about 3 as we expected to see. So yeah, we can see that the passband functions the way that I designed it to, where the gain when it's at its maximum is about 10, but you get a higher gain on lower frequencies because the gain coming from here is larger when it's in the passband on that end, and when it's in the passband or coming out of the passband on the higher end, the gain is going to be lower because the high pass filter has a lower gain than the low pass filter did. At the function of my high pass filter, this one is just a high pass filter, not cascaded with anything. And I designed this one to have the same gain as the low pass filter did on its own, so it's a gain of 5 and a 3 dB frequency of about 800 or 795, I believe. So we're going to test this with 3 different frequencies like we did with the others. We're going to start with a 500 hertz input frequency, same amplitude, 0.5 volts, and we're going to expect that the gain is going to be kind of low because that is obviously outside of our passband. It's below our 3 dB frequency, but it's not significantly lower. If we had tested with about 100 hertz, it'd be a lot lower. But 500, we should see a gain of about 2.6 or 2.66 actually. But we test it, we see the input, give it a second to load. The input is about 0.5 volts as we expect, and the output is about 1.3 volts. So that's a gain of about 2.6, again, similar to what we would expect to see. So now if we apply a higher frequency, 1000 hertz, this is above our 3 dB frequency. So this should be in the passband, but it's not significantly higher, right? It's only about 200 hertz higher than our 3 dB frequency, so it's not going to be the full maximum gain or close to it. It's going to be expecting about a gain of approximately 3.9, something around there. So if we measure this with our 1000 hertz input frequency, we see 0.5 volts as the input. That's good, and it's about a 2 volt output. It's going to be slightly lower, but 2 volts is approximately it. And that gives us a gain of about 4, and that is again pretty similar to our 3.9 gain that we were expecting. Now if we check even a much higher frequency, let's go to 10 kilohertz. We're gonna have to change the scope on this. Maybe turn it off and on again. And give it a second. We see that the input is 0.5 volts amplitude as expected, and the output is going to be about 2.4. So that is a gain of about 4.97-ish, and that is very close to our expected gain of about 4.98. So we can see if we went even higher than that, it would get closer and closer to our maximum gain of 5. And now that we've looked at all of the filters individually, we can look at their rectified outputs. So this circuit right over here is this sub-circuit is the half-wave rectifier for the low-pass filter. This purple wire is the low-pass filter output. This one over here is the half-wave rectifier just for this high-pass filter. And down here, this one at the bottom, is the half-wave rectifier for the band pass filter. That's what the yellow wire carries. So we're going to check this at 3 different input frequencies and see how the outputs are different. So we can look at the outputs on all of these for the input frequency, again, 0.5 volts amplitude and 100 hertz. I'm not going to show an input scope because we've been seeing that consistently. It was up at the top, 0.5 volts. We're just going to look at the outputs here. So here we go. I'm going to give it a second to load up nicely. Okay, so we can see here the rectified output of the low-pass filter for a 100 hertz input frequency is going to be about 2 volts. And over here, and that follows what we'd expect to see with the voltage drop across the diode and with the gain that we observed earlier. And we can see that the peak voltage over here at the rectified output of the high-pass filter is going to be about 140 microvolts. So this is very small, and that makes sense because, as we saw before, the gain at very low frequencies for the high-pass filter is going to be very low, and then there is the voltage drop across the diode. So it makes sense to be a very small rectified output. And over here, we have a, for the bandpass filter, we're expecting it to be lower than this peak voltage, but higher than this one, and that is exactly what we see. It's a peak of about 460 millivolts So that is sort of between the two, and that makes sense. That's what we'd expect to see. Now, if we test this for 1,000 hertz, we're going to see some different results here. Change the scope so it doesn't go crazy like that one is doing down there. And we can see that the low-pass filter over here is going to have a peak rectified voltage output of about 1.6, and that makes sense. That follows what we'd expect to see from the gain and the voltage drop across the diode. The high-pass filter over here, its peak rectified output is about 1.5 volts. Again, follows what we'd expect to see. It's pretty similar to the low peak when we're in this sort of pass band they're both in, but the low is going to be higher, a little bit higher, and this one is, as we can see, it's going to have an average voltage that is lower than the average voltage of this one, because this is higher and this goes all the way down to 0. And we can see in the band pass, the peak is going to be about 3 volts, and that makes sense. A little bit higher than 3 volts, actually. And that makes sense because it's the multiplied gain from both of these, and they're both in their pass band. Well, the other high-pass filter. They're both in their pass band, and we're going to get a nice high gain, and then the voltage drop across the diode, so that's what we'd expect to see. Now, to test for an even higher frequency, let's go for 10 kilohertz. We're going to expect that the high-pass filter is going to have the highest output, peak voltage, and of course the low-pass is going to have a very low one, and the band will also have a low one as a result of that. So give it a second, let the capacitors fully charge. This one is the wrong setting. While that charges up, we can look at the output of the low-pass filter here. So the low-pass filter, we can see it has a very small ripple voltage, right? But the peak value is going to be about 16 millivolts, so that is pretty low. Then that is what we'd expect to see at a really high frequency like this one. The high-pass filter is going to have a peak slightly below 2 volts, and again, that follows what we would expect to see at this high frequency with a voltage gain of close to 5, and then the voltage drop across the diode. Okay, and now we can see here the bandpass filter is again going to have a very low ripple voltage, but its peak is going to be a little higher than the low peak, but still much lower than the peak of the high-pass filter. So that's going to be about 265-ish millivolts. And again, that follows about what we would expect to see. So yeah, we can see that the rectified outputs all do what we would expect them to do. They work the way that I designed them to, and we can see that, if we had, as I said before, if we had an audio input that had, multiple different frequencies, we can see that these would all produce a different output frequency. So if you hooked that up to another audio output source, you would get an interesting distorted kind of synthesized effect with different notes all coming out from the one input audio.